Have you ever hit a wall trying to guess exactly how much data your C program will need to store ahead of time? If so, you've crashed right into the limits of static memory. Well, today in this explainer, we're going to break right through that wall. We're going to completely unpack the definitive concepts, syntax, and structures you need to absolutely master linked lists in C. Here's our quick roadmap. We'll start with the array problem, then build up single linked lists, upgrade those to double lists, look at circular lists, and wrap it all up with a final review. Section 1. The array problem. Seriously, think about it for a second. What actually happens when your array runs out of space? Arrays are, super convenient to declare, and they give you lightning-fast index access. But their fatal flaw? Their size is totally fixed. Because you have to declare that size at compile time, you're basically forced to guess. So you end up allocating an array that's quote-unquote large enough, which just wastes memory if it's mostly empty. Or worse, your program crashes because you guessed too small. Oh, and inserting a new element at the front? It's a nightmare because you have to shift every single other element over just to make room. So this perfectly illustrates the solution we're looking at today. Unlike arrays, which greedily grab memory all at once in one big sequential block, linked lists use a totally different strategy. They allocate memory dynamically, just one piece at a time, exactly when it's needed. This means your list can grow or shrink on the fly while the program is actually running. And since the memory isn't stuck in one giant consecutive block, inserting a new element anywhere is incredibly fast. To pull this off in C, you really have to become best friends with two key functions from the standard library, malloc and free. Malloc is your go-to for requesting memory. When you call it, it carves out a block in the computer's heap and hands you a pointer to it. Now, it does return a void pointer, so you'll usually cast it to your specific type, kind of like int star malloc 100 times size of int. And hey, when you're done with that memory, you absolutely must use free to give it back. That right there is the whole essence of manual memory management. Moving right along, Section 2, Single Linked List Basics. So how do we actually construct the individual pieces of this list? Well, we call them nodes. To build a node, we define a structure. Let's call it slink list. It holds two things, an integer for our data and a pointer called next that points to, another struct slink list. That's what we call a self-referential structure. To keep things clean, we can use typedef to just call this a node. We also set up a start pointer and initialize it to null, which basically represents our empty list before we start adding things. Picture your computer's memory like a map. Your start pointer is hanging out over on the stack. It's just a local variable holding an address. But that address points over to the heap where your very first node lives. Each node in the heap holds its data and then uses that next pointer to chain to the address of the following node. It's like a scavenger hunt, chaining all the way down until the very last node. And to explicitly mark the end of the line, that final node's next field is simply set to null. Let's look at a classic exam scenario, inserting a new node at the very beginning. First, you grab a new node using a function like getNode to get that memory. Fill it with data and set its next field to null. Now, here is the crucial edge case you have to memorize. You must check if the list is empty. If start equals null, boom, your new node is the start. But if it's not empty, you have to point your new node's next field to the current start node first, and then update the start pointer itself. The order of operations is literally everything here. And once you've built this chain, you'll eventually need to read it. Traversing a single linked list means moving node by node, strictly left to right. If you write a while loop to read through, say to print values or find the end, your condition has to check that pointer very carefully. To stop safely at the last node, your condition should be while temp arrow next, not equal to null. That keeps your temporary pointer on the actual list without jumping off a cliff into unallocated memory. All right, Section 3, upgrading to double lists. Single lists are fantastic, but what if you need to search backwards? Kind of like flipping back and forth through a book. That's where we upgrade to a double linked list. We just add a second pointer to every single node. So now we have a right link pointing forward and a left link pointing backward to the predecessor node. It seems like a tiny addition, but it completely opens up the data structure for bidirectional travel. But here's the exam trade-off you absolutely need to remember. Yes, double lists make things like reverse traversals and specific node deletions super efficient because you don't have to scan from the beginning anymore, but it'll cost you. Double lists eat up extra memory for all those extra pointers. Plus, the code gets a lot riskier. Every time you insert or delete, you have way more pointers to juggle, which means way more opportunities for a dreaded segmentation fault. Section 4, Circular Linked Lists. Let's see what happens when we bend the rules a little bit. If you take a linear list and connect the ends together, you get a circular list. There's literally no beginning and no end. By simply coding new node arrow next equals start, you take the last node and point it right back to the first one, creating an infinite loop. The big takeaway here, there are absolutely no null pointers in the main structural links of a circular list. Every single pointer holds a valid address. So why do this? Well, this elegant little loop naturally gets rid of a lot of clunky edge case code. Deleting the last node in a normal list requires special checks, but here the logic is totally smoothed out. Plus, it's just the perfect data structure for modeling systems that naturally cycle, like a computer network ring where data packets are just continuously circulating. And yep, you can do this with both single and double-linked lists. Let's bring it all home in Section 5, Final Review and Takeaways. Let's lock in those trade-offs with a quick cheat sheet. If your program demands fast, random access to data, arrays are the clear winner because linked lists force you to read sequentially. But if you need to constantly rearrange elements, dynamically resize, or insert data on the fly, linked lists completely dominate. Just remember the memory overhead. Arrays have no extra per element cost, while lists cost you 1 or 2 pointers per node. It's all about choosing the right tool for the job. To wrap up this explainer, I'm going to leave you with a quick brain teaser straight from the source text. Imagine a single linked list. How would you manipulate the exact pointers we talked about today to split it into 2 alternating halves, like one list with the even index nodes and one with the odd? It takes some really careful pointer reassignment, and you have to track your next addresses before you overwrite them. Work through that logic step by step. If you can crack that algorithm, you truly understand linked lists. Thanks for hanging out and learning with me today.